Hey, what's up guys? Today we're going to write a summation formula proof using a technique called induction. Alright, here it is. Alright guys, so today we are going to prove this statement here. So we're going to prove that this summation evaluated from k equaling 1 all the way up to some number n is going to equal this expression here for all natural numbers n. So to do this, we're going to use a technique called induction. So these proofs they give a nice change of pace from your typical set theory proofs because these are more procedural, and they also require a bit of algebra, so depending on your preferences you might think that's more or less fun, but they're just a bit different. But the nice thing is you can sort of latch on to this process when you're using induction, which is nice. And so I'll explain what these all mean in more detail when I'm actually writing the proof, but just simply put, your first step is going to be to define P of n, and you're going to define P of n to be the formula you're trying to prove. And the reason we're going to do that is just so we don't have to refer back to that. You don't have to write all of that formula out every time you want to refer to it. So this is just going to be sort of just a writing convention. And then how induction works is you first start with what's called the base case. And this is when we're going to manually prove that P of 1 holds true. And what that means is that your formula holds when n equals 1. So, and again, I'll explain what this means when we're doing it, the actual proof. And then once you prove the base case, our job is going to be to prove the implication that P of n holding true implies that P of n plus 1 holds true. So in other words, we're going to suppose, just like we would prove any conditional statement, we're going to get to suppose that P of n holds true for some natural number n. And then it's going to be our job to show that P of n plus 1 follows. So in other words, if your formula holds true for the nth case when n equals, in this case, n, then it must follow that the n plus 1 case will also hold. So that's going to be our job to show that. And then finally, once we do that successfully, we're going to be able to conclude that P of n, the formula, holds for any natural number n. All right, so let's go ahead and get into this here. So again, our first step, it's gonna seem trivial, but again, it's so we don't have to write this over and over and over again. Our first step here is going to be to define P of n. So we're going to let P of n be the statement, and then we're just going to copy down our formula here. Because again, this is an equation, so equations are mathematical statements. Okay, so that's step 1, is to define P of n. And now step 2, as I mentioned, is going to be to manually prove that P of 1 holds true. And again, this is called the base case. So all we're going to do now is we're going to, since we're just worried about the case where n equals 1, we can actually drop the summation because we're not going to have to add anything to our expression here. So all I have to do is just substitute 1 in for my k's and substitute 1 in for my n's, and then I have to make sure that those two things do in fact equal each other. So I'm going to substitute 1 in for my k's here. And now I'm going to substitute 1 in for my n's here. Okay, and now let's verify that this does in fact equal each other. So we have 1 times 2, which is just 2. And then here I have 1 times 2, which is 2, times 3, which is 6. And then 6 divided by 3 also gives me 2. So I know that this checks out. And so we can say that P of 1 holds. All right. So now this is sort of the challenging part of the proof. We need to now prove that P of n being true leads to P of n plus 1 being true. And so, again, this is a conditional statement. So we get to suppose the hypothesis. We get to suppose that P of n holds for some n in the natural. So we'll go ahead and do that. Okay. And now, in order to show that P of n plus 1 holds, it's important to know what P of n plus 1 actually is. So let me write that out first. So again, P of n plus 1 is going to be this summation, but instead of stopping at n, it's going to stop at n plus 1. Okay, so again, instead of stopping at n, we want it to stop at n plus 1. And now it's important to note that this summation stopping at n plus 1 is going to be the summation stopping at n plus the n plus 1 case. Again, I'll say that again. This summation stopping at n plus 1 is going to be the summation stopping at n the summation stopping at n plus the n plus 1 case. And so what I'm going to do now is I'm going to add to this summation this expression, but I'm going to substitute n plus 1 in for my k's. So instead of a k, I'm going to write n plus 1. And then instead of my k plus 1, I'm going to write n plus 1 plus 1, which is going to be n plus 2. Okay, so all I did was I substituted n plus 1 in for my k's, and I added that case onto the summation ending at n. All right. So now how exactly do we prove that the P of n plus 1 holds? Okay, so now I'm going to switch to some scratch paper here. This is not part of the written proof. This is just scratch work to help get our thoughts on paper. Our job is to show that P of n plus 1 holds, okay? So we already suppose that P of n holds. So we know this is a true statement, okay, for some n in the natural numbers. To prove that P of n plus 1 holds, we need to show that the summation stopping at n plus 1 equals what the summation stopping at n equaled, except instead of n's, we have n plus 1's. So I need to substitute an n plus 1 in for all of these n's. Okay, So again, all I did was I substituted n plus 1 in for all of my n's here. And now I'm going to simplify that. So n plus 1 is just n plus 2. And n plus 1 plus 2 is just n plus 3. And so this here is what I need to show that this summation evaluated from k equals 1 to n plus 1 equals. All right, so if I can do this successfully, if I can show that this equals this, then I'll have it. And so keep this in the back of your mind here. All right, now this is what we call the induction step. So notice how this is not what I wanted to show, right? I wanted to show that this here equaled this thing. Okay, not this thing. So I need to think of a way to get all of this in terms of n's, because notice how what I showed here, all I had was n's. I didn't have any summation notation here. I didn't have any k's. I just had everything in terms of n, or really n plus 1. So I need to get this in terms of n. So how I can do that is I can use a substitution. So since I know what this here equals, because I suppose that p of n holds, right? I suppose that p of n holds for some n in the naturals. So I know that this statement is now true, because I supposed it to be true. And so notice how this is the same as this. And so what I can do now is I can make a substitution. I can get this expression, which is in terms of n, and I can substitute it for this expression here. Okay. So, and again, our induction hypothesis was proving that p of n held. So by the induction hypothesis, we have that this summation stopping at n plus 1 is going to equal this here, but I'm making the substitution. Okay. Now I have everything in terms of n, and now my job is to show that this here, this giant expression, is equal to this. Okay, so this is where our algebra skills have to come into play here. So first thing I'm going to want to do here is I'm looking at structure here. So I'm seeing this, I'm seeing this, which is just one giant fraction, right? So I'm thinking maybe for this, I should probably get everything over one denominator. So I'm going to try to create a common denominator of 3 here, so I can combine these into one fraction. And so I'm going to put all of this over 3. And if I want to do that, I also need to multiply the numerator by 3, right? Because 3 divided by 3 is 1, and so I haven't actually changed the value of that expression. And now what this will allow me to do is, since I've common denominators, I could put all of this, these numerators, into one single numerator. All right. And now, again, we're pretty close here, because I had everything over 3 here, just like I do now. So how do we make that numerator look like the numerator that I just showed you? And it turns out we have some common factors that we can factor out. So notice how in this expression here, in this product, I have an n plus 1 and an n plus 2 as a factor. And I also have an n plus 1 and an n plus 2 as a factor over here. So I can factor those out. Okay, so that's me factoring out the n plus 1 times n plus 2. And then that's going to leave me, when I do that factoring, the distributive property tells me that I'll be left with a factor of n plus 3. Okay, so don't lose sight of what we've done here. We've shown that the summation ending at n plus 1 does in fact equal this expression up here, except wherever there was an n, there is now an n plus 1. So we've shown that p of n plus 1 holds, and again this was as a result of p of n holding. And so now we can conclude that p of n will hold for all numbers that are natural numbers. And the reason we're allowed to conclude this is because of the fact that we proved the base case. So remember, we proved that p of 1 held, and then when you combine that with the fact that we prove that p of n leads to p of n plus 1 holding, well, since p of 1 holds, that must mean that p of 2 holds. And if p of 2 holds, that must mean that p of 3 holds, and so on and so forth. And this creates a giant chain reaction that essentially proves that any number in the naturals will satisfy this formula. All right. And with that said, guys, it's been demonstrated.